Hi, my name is Jiewen Hu. I'm a second-year PhD student in CPAS. Today, I'm going to talk about a high-density, low input-to-output capacitance, multi-channel GaN power supply for gate drivers of 10 kV, 240 amp silicon carbide MOSFET modules. In recent years, there is a clear trend towards increasing demand of electric power in the area of high-power applications, which is widely used in the industries such as transportation, power, and energy. Recent breakthroughs in silicon carbide materials and fabrication technology have led to the development of power device, which is expected to revolutionize power distribution and conversions because of its higher breakdown voltage, higher thermal capability, and lower on-state resistance compared to its silicon counterpart, along with its good high-frequency performance. But it also brings some challenge to the gate driver. The gate driver should have a carefully high-voltage, high-density design. It should also have good EMI mitigation and containment, as well as the reliable performance. This required an isolated power supply of the gate driver to be able to sustain high isolation voltage, to have a low input-to-output capacitance to reduce the CM noise, and to be able to output a constant voltage. The specifications are shown in the table. Electric assemblies must satisfy strong safety regulations regarding creepage and clearance distance. The electrical clearance is the shortest distance through the air between two conductive elements, whereas the creepage is defined as shortest distance on the surface of an insulating material. In order to increase the creepage path without increasing the size, a popular technique is to insert a slot to PCB, and then the shortest creepage path will be the one along the transformer core. In this case, the core needs to be large enough to provide sufficient creepage distance. To reduce the transformer core size, and meanwhile to satisfy the critical standard requirements, a transformer structure with single turn at the primary side is proposed. The purpose of this winding design is to separate the low voltage and high voltage interfaces into two wards. By designing one of the two coils turn number into 1, that coil becomes a conductive cable and it can be extended as needed. The creepage path is mainly the path along the cable instead of the transformer core. Large core is no longer needed. The second critical challenge is the low input-to-output capacitance design. As the gate driver circuit is sensitive to high CM-dV/dt, the model of the input-to-output capacitance has been built and analyzed. The dimensions of the transformer can be optimized, and the 1.55 picofarad input-to-output capacitance is measured. In order to reduce the switching loss and push the switching frequency to a higher level, resonant converter is necessary. The resonant tank at the primary side aims to achieve source switching, load independent, and to cancel the large leakage inductance caused by the long primary cable. Resonant at the secondary side aims to maximize the power transfer capability. The complete circuit, which is called LCCL resonant converter, is shown. RCR are in resonant to build a resonant corpus for the transformer primary side input, which can present current source characteristic. LSCS are in resonance to enhance the power transfer capability. This is the 6.5 kV power supply from concept. It satisfies 60 mm creepage distance and has a 4 picofarad input-to-output capacitance. This is the primary converter board, and this is the secondary converter board. We can see that the insulation voltage is increased and the input-to-output capacitance size is significantly reduced. This is the test prototype. Primary converter board is on the left. This is the high voltage cable. These are two secondary converter boards. Because of the advantage of resonant current bus, two secondary converters can share the same high voltage cable, which reduces the number of primary converters. This is the verification of the zero voltage switching. This is the gate signal of the bottom switch. This is the gate signal of the top switch. And this is the drain source voltage of the bottom switch. We can see that the drain source voltage reached 0 before the gate signal arrived. Similarly, the drain source voltage reached to a high level before the gate signal arrived. This is the verification of load independent. These experiment waveforms are for one load condition. This waveform is the current in the resonant current bus, and this waveform is the secondary output current. This is the output voltage. We can see that the output voltage reached 28 volts and the power here is 10 watts. These experiment waveforms are for two load conditions. These two waveforms are the two output currents of the transformer secondary side, and these two waveforms are the output voltage for the two secondary converters. We can see that the output voltage reached 28 volts and the power reached 10 watts. Thanks for watching. For more information, please visit our website.